Okay, so we'll start. Okay, so we have this week is kind of simple, so there isn't much to cover in this week. We've already seen all of it in the lecture, so we'll very quickly go through this, and if there are any doubts, we can discuss them. Okay, so we start with this 0-1 loss, right? So there is any classification problem. If you look at, we have the 0-1 loss is the average number of errors that are made. Okay, now the way it is given is 0 if W transpose XY is greater than or equal to 0 and 1 if it is less than 0, right? So we are looking at the case of linear models, right? So we are trying to understand all linear models and the laws associated with each of them. So why are there so many linear models for classification, and how can we understand all these models from the perspective of the loss function associated with them, right? So if you through this session, we'll be using this U for W transpose X into Y. Okay, that's convenient every time. Otherwise, we'll have to call it W transpose XY, W transpose XY. Right? So we'll just call that U. Okay, so in terms of U, this is a function of U, right? Now W transpose XY, this whole thing can now be treated as a function of U. So this is just 0 if U is positive and 1 if U is less than 0. So U is less than 0, there is some misclassification. The point falls on the wrong side of the decision boundary, and this is what you have. Okay, so this is the 0-1 loss. I hope this everyone is clear about this part. Okay, and the problems with this loss is that it is not convex, therefore optimizing it is going to be hard. Right? So even for a linearly separable problem, if you want to find the linear classifier, sorry, not for a linearly separable problem. For a linearly separable problem, we already know you have perceptron, you have hard margin SVM, so there's no problem there. But if you have a general data set which is not necessarily separable linearly, optimizing or minimizing the 0-1 loss is going to be hard. Okay, which is why we come up with different loss functions and associated models to approximate or get around this problem. Okay, so the first thing is squared loss. So what is this? What is the formula for this squared loss in terms of W, X, Y? We have already seen it. It's W transpose X into Y. So it is W transpose, yeah, W transpose X minus Y whole square, right? So the, for example, this, so why is this W transpose X into Y? Let's quickly draw that part, right? So you have, let me draw this. So you have the origin here, and your classifier would be something like this, right? So this will be W, and for any point here, this, not exactly the distance, but the projection, right? Some kind of a projection is what you get when you do W transpose X. Of course, you have to do norm W, you have to divide by norm W and all that, right? So, but if you're only looking at a rough estimate, it's W transpose X, right? So this gives you how far away you are from the boundary, right? So this is W transpose X, and for all points on this side, you want it to be green or 1, okay? And for all points here, you want it to be -1, this is red. Okay, so W transpose X minus Y whole square, if you try to minimize that, sum of that, that will give you one loss for classification. But this is a bad loss, as you already know. So this is not really a good choice, because if you have a point that is far away here, okay, so this distance is going to be really high, right? So, and it's
Very
correctly
useful.
right. So even though it's correctly classified, it has a label, true label of y equal to 1, correctly classified, yet you are going to penalize that with this much loss, right? Which is unnecessary. So this is a bad choice for classification, but still we'll go ahead and express this in terms of u. Okay. So this is, you expand this, you get this w transpose x square plus y square minus 2 times this. Okay. So this can be replaced with u, right? This can be replaced with u. And what else can you do? So you can just add a y square here. So what allows us to add a y square here? Because y
It will be
square is
equal to 1. Because of that only we are privileged to add y square because it will result into 1.
right. It is 1, right? So you can add y square here and you can replace this y square with 1. So if you do that, you notice that what happens is this is w transpose xy. So this is u square and this is minus 2 times u. W transpose xy is u, right? So this minus 2 times u and you have 1 here. So this becomes u minus 1 whole square. So if you now plot this as a function of u, it's a quadratic curve, right? So center at 1, at 1 it is 0, and then it is this is the form it takes.
Sir, how we get that one there?
Because y square is 1. Y is 1 or minus 1. So
Okay, so you are substituting that value.
yeah. So I'm just same thing that Prof did in the lectures. I'm just repeating that. So this week there's nothing much to do. Okay, so u minus 1 whole square. So this is one convex surrogate for the 0, 1 loss, right? So 0, 1 loss was this, which is not convex, but this one is convex, right? So this is a squared loss. So squared error or squared loss is a convex substitute for 0, 1 loss. But it's a bad substitute because it doesn't handle outliers well. For points that are already correctly classified, it's going to penalize. So for example, the moment u is greater than 0, you know that all points here, right? So u represents the outcome of your classification, right? So whenever it is positive, you have correctly classified, and whenever it is negative, these are all misclassified. So this region is misclassified region. You notice the amount of error it is assigning to points that are correctly classified, right? So it keeps on increasing. So this is a bad model to have. Okay, so that is squared loss. Now what we had for the hinge loss is SVM part, right? So it was max of 0 comma 1 minus w transpose xy, right? So we saw this yesterday. So it's very simple to substitute u here. Okay, now all that you have to do is max of 0 comma 1 minus u. And when will this be positive, or so when will this be 0? When this is, so 1 minus u is less than 1, right? So that's when it will be, sorry, less than 0. So when will 1 minus u be less than 0? When 1 is less than u, or I made a mistake here. No, so I'm talking about this. Yeah. So when is 1 minus u negative? When u is
Greater than 1.
greater than 1.
Greater than
So
one.
that is this case. And the other one. So when 1 minus u is when u is less than 1, 1 minus u is going to be positive, and therefore you will end up with this particular curve or piecewise linear function. Okay. So this is another convex approximation to your 0, 1 loss. And notice that this is far better than the squared loss, because for all these points which are correctly classified, the loss is 0, as it should be, right? It's kind of like, that's what you expect. But then why do you think here the loss is non-zero, right? For this region, even though it's correctly classified, the loss is non-zero. Why is that the case? Shouldn't this also be 0? Why is this non-zero?
It's almost like a margin concept. I think, just to boost the confidence, I think you need to have some buffer.
Yeah, this is because of the margin, right? So in SVM, recall that we want the classifier to not just classify it correctly, but we also want the points lie beyond the margin, right? So the constraints are W transpose XY greater than or equal to 1, right? So this contributes this. There is some loss here because these are all points which are classified correctly, but with margin less than 1. Okay, so please note that this region, right, this triangular region is, let's write it down. So what is this? This is classified correctly.
Functional margin.
Yeah, with margin less than
1.
Okay, so please make a note of this. This is something we need to know, right? Even though it's correctly classified, it can still have some loss depending on the kind of model that we are dealing with. Okay, so that is the hinge loss. We call this the hinge loss. The loss which was associated with logistic regression. So that is what? That is, we actually motivated it using log likelihood, right? So it was a probabilistic model. It is a probabilistic model. So we kind of try to do it. We used MLE, right? So that's how we obtained the parameters. So we said that the negative log likelihood is the loss. Okay, so this is called the cross entropy loss. So this we'll spend some time on this. So how did we get here? If you recall this particular, what was happening in logistic regression? We were trying to, what were we trying to do? So we have the sigma of W transpose X, right? So this is what? This is actually probability that the data point that you see as predicted label is 1.
Sir, sigma is the sign function.
No, sigmoid function.
Okay.
That 1 by
0 or
1
1.
plus 1 by 1 plus e to the power minus whatever sigma
Right.
W by X.
Yes, yes.
Right. So this was the probability that we associated with the predicted label being 1, and 0 is just 1 minus this, right?
1 minus.
So this is what we had. Now this can be seen as tossing a coin, and with this probability, so given X, you can compute W transpose X, and then you can take sigma of that. So sigma of that will be what? It will be 1 by 1 plus e power minus W transpose X, right? So you do all this, you will end up with some value. So, and that's the probability with which you can actually generate also, right? If you think about how this label was generated, you can think about it that way also. Now, when we are doing MLE, what did we do? We did negative log likelihood, right? So first of all, log likelihood. So what is the log likelihood going to be? So if you remember, for one data point, it's p power y into
1
1
minus
minus p power
1 minus 5.
1 minus 1.
right? So this is the form that the likelihood takes, right, for one data point. So because if y is 1, then the likelihood of seeing that is just p. Okay, that's the probability with which y will come up. Y equal to 1 will come up, and it's 1 minus p. So what you do is, instead of p, you plug in sigma of W transpose X over y into 1 minus sigma of W transpose X over 1 minus y, right? That's what you end up doing. So this is the likelihood for one data point. So the log likelihood is going to be just y log sigma of this whole thing, right? So W transpose X minus 1 minus y, so sorry, plus 1 minus y in log of 1 minus sigma of W transpose X. Okay, so this is what you had. This is the log likelihood. Now what you need is, this is not a loss, right? This is, you are trying to maximize the log likelihood. So if you want to extract the loss function out of this, you need to take the negative of this and minimize that, right? So that is just the whole thing, but the negative sign appended or prepended here, right?
That is just to convert the maximization problem to minimization problem.
Yeah, but fortunately, you can also view this as a loss function. So this is called the binary cross entropy loss. Okay, so this cross entropy function takes the following form. It takes the form minus y log y hat, okay, minus 1 minus y log 1 minus y hat. Okay, so where y hat is the predicted the probability associated with. So in fact, you should not call it y hat. Better to call it the probability associated with the prediction being 1. Okay, so that's what we have here. If you notice, this is probability that this will be predicted as class 1, and this is probability that it will be predicted as class 0. Okay, so it's called binary cross entropy. You can see why it is called entropy, why entropy is coming in here. So for decision trees, what was entropy? It was minus p log p minus 1 minus p log
1 minus p.
1 minus p, right? So this is entropy, which we call h of p. Okay, so there is only one distribution here, which is the Bernoulli distribution with parameter p. So this is just entropy. Whereas here you have kind of two distributions, right? So one associated, so I shouldn't be actually calling it y, but please don't mind that. So why this is called cross entropy is because you have two different probability distributions in some sense. So one associated with the true label. So y can be only 1 or 0, but this p can be anything between 0 and 1, right? So there's a cross entropy. So this is also looking like entropy, but then between two distributions. Okay, so is this clear why this is called binary cross entropy? Roughly, not in a very exact sense, but
Yes, sir.
okay. So what we are doing is, this is the loss. So how do you understand? This is actually a nice way to understand this loss. So you can look at what happens when y is equal to 1. So when y is equal to 1, the true label is 1. So this loss becomes
Minus y log p.
yeah minus y
Minus
log.
y log.
Yeah, it becomes just minus log p, right? Or let's look at
Oh, y
this.
is 1, correct. That's right. Yeah.
Right, so it just becomes minus log sigma of W transpose X, right? So this, the larger the value of sigma of W transpose X, the smaller the loss. Okay, so larger this predicted probability, right? This is your predicted probability. Smaller the loss, or instead of calling it larger, I'll call it, better to say, closer sigma of W transpose X is to 1, smaller the loss. Why is it small? Because
You're confident
log
on
of
your classification.
Log of that value is 1 by that value, right?
this is close to 1, right? If this is close to 1,
Mhm.
log of that is close to 0, right? So this
Yes.
is smaller the loss. Now, for when y equal to minus 1, by the way, this is positive, right? So this is, you must note that this is greater than 0, because this is a fraction. The log of that fraction will be negative, so negative of that will be positive. So this loss is always positive. So when y is minus 1, what happens? The loss becomes minus, this term vanishes because y is 0. Sorry, when y is, okay, so there's a small problem, right? So you have to use 0, 1 here, okay, which is what we'll be seeing. So you have to transition from 1, 0 to 1 minus 1, but for now it's 1, 0 here, right? So what does the loss become when it is 0? Minus log,
Log 1 minus p.
this is the loss, right? So now notice that this is the loss when y is 0, right? For a for true label being 0. So when sigma is, so what do you want the prediction to be? Prediction, this is the predicted probability of the data point belonging to class 0, right? So sigma of
0.
W transpose X is always predicted probability of it belonging to class 1. So you want this to be close to 1. Or rather, you want this to be close to 0. So you want 0. What can you say about the loss in this case?
It's greater.
No. So what I'm asking is, as T, this is the predicted probability that the data point X belongs to class 1. So when this is very small,
Then log of that will be also 0, right? Because 1 minus 0 is 1, log 1 is 0.
yeah.
Yeah.
So same situation, right? So
Yeah.
notice that these are opposite things. So for y equal to 1, the loss looks like this. And what is ideal is for sigma of W transpose X to be close to 1. Predicted probability should be close to 1. When y is 0, we want the predicted probability of this being 1 to be close to 0.
Sir, can you explain again? Means I'm not getting
Which part?
this. Why it could be 0, then smaller the loss.
Same, right? It's just
Linearly
algebra.
separable. Both are. So that's
So,
why loss is 0. Both.
yeah, so if this is 1, if this is close to 0, this is close to 1, right? The whole thing.
Yes, okay, it will be 1 if I say like sigma W transpose X is equal to 0.
Yeah, so that's what we are looking for. That's what we need, right? So when should the loss be high? The loss should be high when there is a misclassification, right? Or when you are not doing a good job, loss should be high. So if this quantity is big, so closer to 1, that is when the loss will be high.
Because that value will be very close to 0. 1 minus that value is close to 0, and that's why the value will be
Yeah,
small.
so that's right. So you have to understand two things, right? One is the algebra, which is important, but then more important is how do you interpret this binary cross entropy loss?
Sir, y is plus 1 or minus 1 now, sir? How it is 0, sir?
And in this case, it is 0. So here in this formulation, we are taking the label to be 1 and 0. We'll soon transition to 1 minus 1.
Okay, sir.
There was a question associated with this. So I was not able to fully grasp that. So, like, can you take an example where it is 1 and minus 1, considering Z as it was explained in this one?
Yeah. So that's what we'll be going to next. So see, this is the loss when you have the labels being 1 and 0, right? This is just what we saw. So the true label is 1, the loss is this quantity. If it is the true label is 0, the loss is this quantity. Okay. Now what we are doing is again some algebra. That's all we are doing. So log of sigma of W transpose X is just log of 1 by 1 plus e power minus W transpose X, and then you just bring the minus sign out. Okay. So 1 minus sigma is sigma of minus something. Do you remember that? Sigma of a some quantity, or sigma of minus some quantity is 1 minus sigma of the same quantity. Okay, so you can understand it that way, or alternatively, you can just
Can you
know this.
repeat what you said?
We discussed this, no, 2 sessions back. Sigma of minus z is 1 minus sigma of z. Last few minutes of one session, we discussed this. But anyway, that's not needed. So what you need is this part. This is clear, right? This is how you got these two.
So below part minus log 1 plus e to the power Minus is okay. It's when we solve this 1 minus 1 upon 1 plus e to the power minus w transpose x is equals to e to the power w transpose x upon 1 plus e to the power minus w transpose x.
No, you will have e power minus w transpose x in the numerator also.
Numerator, yes, sir.
And then you will multiply by e power w transpose x in the numerator and denominator. That will give you
Okay.
1 by 2. It will
Yes.
give you w transpose x.
Yes. Okay. Clear, sir.
Okay, so that's all we are doing here. So if you plug this in now, when z equal to 1, this is what you have, and when z equal to 0, this is what you have. So this is the true label, right? Now you can easily move to y equal to 1 and y equal to minus 1. So this corresponds to y equal to 1, and therefore you can multiply this by y. This corresponds to y equal to minus 1. Therefore you can multiply this by minus y. Once you do that, you end up with a uniform formula for both situations.
Sir, not understanding means you the second line. Can you explain again?
You tell me what, so same thing in the lecture I'm repeating. So you tell me what is not clear.
Actually, I didn't understood the logistic laws in the lecture itself, but now I am understanding somehow. So this log of 1 plus e to the power minus w transpose x, you said that we will multiply it with positive 1 for y is equal to 1.
No, you tell me what you understand from these equations. Or rather, what is it you don't understand in these steps? Only then we can, so I don't get the confusion actually. What is the confusion here?
This z, that is w transpose x.
No, z is not w transpose x, right? Z is a label.
Okay, so we will multiply z with this log function.
So
No,
you make a last universal for this with respect to y. If you put the y is equal to 1, so that is going to be z is equal to 1. If we put the y is equal to minus 1, then we got the z is equal to 0.
correct. Yeah, z is not w transpose x.
Yes.
Z is label in this case.
And y is w transpose x then.
No, y is also the label.
Maybe the thing is logistic regression is a discriminating function, right? So we always predict the probability of a label given the data. I think that is probably what the disconnect is.
Yeah, so see, y is always labeled, right? So we never say that y is w transpose x. The probability associated with y being 1 is sigma of w transpose x.
Because it's discriminating, right? So we are always saying probability of y equal to 1 given the data, right? So it's a discriminating function. So I think
So
there
z
are two
and y are
values.
used interchangeably here then.
And
Means if I
no,
say y is equal to our true label.
z and y are both labels, but then z is 1 or 0, y can be 1 or minus 1. So z is 1 means y is 1. Z is 0
Okay,
means y is minus
minus
1.
1. Okay, okay, okay.
So generally the pattern we have seen, if it is a discriminative model like a logistic, for convenience binary entropy laws and all that, we conveniently choose 1 and 0, that works. But
Right.
if it is we are predicting the class directly, like let's perceptron, then I think it's a sign and all that, right? So there it is +1 and a -1. I think we have to understand that depending on the loss function and all that, then it is chosen conveniently so that the mathematical expression and the calculations becomes easy.
Right.
Yeah.
Okay, so that is, so you get log of 1 plus e power minus u. It boils down to something very simple. So that's for logistic regression. Okay, and this is how it looks. So you use log to the base c here, and you end up with something like this. All right, so this is the logistic loss, and finally you have this loss associated with the perceptron. So perceptron, we didn't have a loss function actually, but then we can think of it as a loss function. So the loss function is nothing but minus transpose w minus w transpose xy when the point is misclassified. Okay, so you can impose this as the loss, and if you actually plot this, this is very similar to the hinge loss that we had. And then it's shifted to the left by 1 unit. So the perceptron is not going to worry about the margin. Anything that falls on this side, it's going to classify it. So it's going to say it's correctly, there's no loss, right? All correctly classified points do not suffer any loss under perceptron. Okay, so how does this come about? You can think of this as doing stochastic gradient descent with this loss, okay, on a single data point. So this is what it means. For a single data point, this will be the loss, and you set the learning rate to be 1. If you take the gradient of this, what will you get? Minus xy, right? So that's what you
With
get.
respect to W,
Yeah, the
we have
gradient of loss with respect to W, whenever the point is misclassified, is xy. At other times, you can use 0. So there are no updates when the point is correctly classified. So all other times, it's the gradient is minus xy. Since you are doing gradient descent, it will be wt minus xy. So wt plus xy. So eta is 1. Safely, we have assumed that it is 1.
So if you look at the graph of these loss functions, right, for perceptron and SBM, the only difference is it's shifted by 1, right?
Right.
Otherwise, they're similar. Whereas for logistic, it's a smooth exponential. So it's just looking at these loss curves, we can guess what is the the model actually, right?
Right. Yeah.
Yeah.
Okay, so those are the 4 losses we are mainly looking at. So if you now combine all of them together, these are all each of them is associated with one classifier, right? So this is the 0, 1 loss, and this is your hinge loss. This is logistic regression, the logistic loss, and you have your perceptron loss, right? So whatever you call it, so that's the loss function associated with this. So these give you the 4 convex surrogates for the models that we have seen.
This is an end-term question.
I don't know. So these are the loss functions. Okay, so that's all there is to this lecture in this part in week 12. Okay, so we can actually move on to
the last part. The rest of the 2 lectures which followed after that won't be there.
no, we are coming to that. Neural networks is there.
Okay.
Yeah, so we'll discuss that also, and after that we'll close. So that part is also there.
Okay. So it is a part of intern.
Yeah.
yes.
Okay, very quickly we'll go through this. So there's nothing much in week 12, as I said. So it's more of introduction to some ideas. That's all, right? So the neural network is, you can think of neural networks as some kind of an extension to perceptrons, right? You are starting from perceptron and building it up. So perceptron is what? It's just one decision unit. It accepts some input and it returns one output, right? So it's 1 or 0. So if you stack these perceptrons across layers, you get what is called a neural network. Okay. So every neural network has what is called a network architecture. So in this toy network, there are 2 neurons. So we call these neurons. So all these circles are going to be called neurons. So there are 2 input neurons, and they feed into what is called a hidden layer. So this hidden layer is having 3 neurons. Okay, we call these hidden layer neurons, and connecting them is, so connecting the neurons between layers, you have some connections, right? So let's just call these connections, and these connections are going to have some weights. For example, for the first hidden layer and for the first neuron in the first hidden layer, there are 2 connections coming from the input. Okay. Likewise, you will have two connections to the second neuron and to the third neuron. Okay, these are all independent connections. So they're not dependent on, for example, this connection is not dependent on this. Okay, so this is coming from this input, this is coming from this input. Okay, if you plug all these things together, you have 2 into 3, 2 neurons here, 3 neurons here. So you get 6 connections. So 6 weights. So each of these is going to have a weight associated with it. So there are going to be 6 weights. Okay. So likewise, you continue this. So you have one more hidden layer. You can have as many hidden layers as you want. And this hidden layer is going to have how many connections? These two layers between them. Same 6. Right?
6.
Same 6. Okay. And then finally you end up with an output layer. So this is called the output neuron. Okay. So in this case, there is only one output and we call that y hat. And depending on what the value of y hat is, you could either use it for classification or regression. Okay, so y hat is a real number. We'll call it a regression network. If not, it will be a classification network. Okay, y hat is 0 or 1. This is the basic idea. Now we look at the weights. Okay, weights are what are weights store the what you learn from data. Okay, so learning from data. So whatever you have learned from data, that information is going to be stored in the weights of the network. So the strength of the connections, you can also view weights as the strength of the connection between two neurons. So if this is, let's say 2, this is 3, this is 1, then this particular connection is stronger than the other two. That's one way of looking at it. Okay, so those are weights. So we'll have another kind of parameter called the bias. Right, so the bias is associated with all hidden layer neurons. Okay, the bias, there's no bias associated with input neurons. Okay, but for all other neurons, you'll have some bias associated with it. So even for the output neuron, you'll have some bias, right? So if you notice, you have 1, 2, 3, 4, 5, 6 biases. And how many weights are there in total? You have 6 plus 6, 14, right? So you have 14, let me mark it using a pen itself. So there are 14 weight parameters. So how did that come about? So that is 2 into 3. So that is the number of connections in the first hidden layer. And then from first hidden layer to second hidden layer, you have another 3 into 2. And finally, from the hidden layer to the output layer, you have 2 into 1. Okay, so that's 12 plus 2, 14. So these are 14 weights. Okay, so these are 14 weights, and how many biases are there? 1, 2, 3, 6 biases are there. So you have 20 parameters. Okay, so this network has 20 parameters. 14 of them are weights, 6 of them are biases. So how many neurons does it have? It has, so 2 plus 3 plus 2 plus 1. So 3, 4, 5, 6, 7, 8. So it has 8 neurons, 2 input neurons, 1 output neuron, and 5 hidden layer neurons. Okay, again, I'm just repeating this. The input layer does not have any concept of bias associated with it. It is only associated with the hidden layer neurons and the output neurons. Okay, so now we come to this activation function very soon when we actually start looking at how information flows in a network. So you can also view a network as the AG. Right? What is this? For those of you who have
Direct acyclic graph.
Yeah, this is a directed acyclic graph, right? This is a graph. So a neural network is a graph. So what kind of a graph is it? It's an acyclic graph, meaning there are no cycles. So for example, if you have a connection from here to here, there is no connection going back here. Of course, in this type of network, it is not there. There are different kinds of networks. Some of them have these what are called residual connections. So they'll be going back. But for this network, there are no cyclic connections. So all connections are from left to right. Okay, and it's a directed graph, meaning the edges have directions. Okay, so you can view it that way also. Of course, this maybe direction part you can leave it, but this direction is useful to understand that information is flowing from input to output in this way. Okay, so that is the idea behind a network architecture. The number of parameters, what are called neurons, what are hidden layer neurons, and all that. Okay, so let's move on and let's look at how information is actually going to go. Okay, so assume that you have some input x1, x2, and you have this weight is 5, this weight is 3, and this bias is 2. So how is information going to flow from the input layer to the first hidden layer neuron? Okay, so what you do is whatever input you get, you are going to linearly combine it. So meaning similar to what you did in perceptrons, right? W transpose X. So you are going to do W1 X1, that is 5x1, plus W2 X2 is 3x2, plus B. So in so far we have not seen this B anywhere, but then we are going to see this bias in this case. So this 2 is called the bias, right? So you compute this. So this is a linear combination. Okay, this is W transpose X plus B, followed by what is called an activation function. Okay, so this is what is there in this slide. So there are two types of activation functions. One is called ReLU. So what this ReLU will do is whatever comes in, if it is positive, it will retain that positive value. If it is negative, it will just substitute that with 0. Okay, so let's just do one example here for this. This is g of pi x1 plus 3x2 plus 2. Right? So this is it's going to look like g of pi x1 plus 3x2 plus 2. Okay, so if the input to the network happens to be, say, x1 equal to 1, x2 equal to -2, for example, what will happen is you will first do the linear combination. So you'll do 5x1 plus 3x2 plus 2, which will turn out to be 5 minus 6 plus 2, right? So this is what? A 1. Right? So now your output, the what is going to be computed at the hidden neuron is g of 1. So if you are using this ReLU, this will be g of 1 will be ReLU of 1, which is
I think max of 0 and 1. 1.
1, right? This will be 1. Instead, if you use the sigmoid activation function, g of 1 will be sigma
1
of 1.
divided. 1 by 1 plus e.
Yeah, it is that whatever we have been seeing so far, right? 1 by 1 plus e power minus.
Minus 1.
Right? So that is if you use sigmoid. So this is what? This is the computation associated with one neuron. Okay, so there are two steps that you have to remember. One is linear combination followed by an activation. So this makes the entire network a nonlinear function of the inputs. Okay, so far what we have been seeing is all our classifiers have been of the form W transpose X. Of course, we kernelized in some instances, but then generally it is some function of W. So you have some h, right? So h learns some function from RD to 1, and usually this h has been of the form W transpose X, right? It has been a linear function, and that is too restrictive, right? So you can't expect all data sets to have linear structure. So you need a function that is non-linear, okay, in the inputs. So a neural network is one such function. Okay, and how is this non-linearity achieved?
Due to composition of functions.
And not just composition. So if you combine a lot of linear functions, you will still get a linear function, right? So you are by composing non-linear functions, right? So this activation is a non-linear.
That's what I'm
Yeah, but it's not just composition, right? So composition of non-linear functions.
saying.
Right?
Overly.
So, yeah. So it's linear combination followed by non-linear activation. That's what gives you that's the power behind a neural networks, right? So this can therefore learn all sorts of non-linear boundaries it can learn to come up with. So let's go back. So this is where we were, right? So this, if you use ReLU, this becomes max of the linear combination comma 0. If you use sigmoid, it's sigma of this quantity. Okay, so why is this called bias? So there is another reason why it's called bias. So you can think of it this way. So this is the linear combination, right? So if you have this linear combination followed by activation G, what happens? So the bias can be understood as what happens when the inputs are 0. So when the inputs are 0, you have G of 2, correct? So assume that this is ReLU, right? So it's ReLU of 2. So this is kind of telling you the bias tells you or gives you a sense of an idea of how willing this neuron is to fire. Okay, so a neuron firing means, think about it this way. So if this input is positive, then the neuron fires, meaning it returns some positive value. So neuron firing means you can think of it as returning some positive value. Okay, for now. Right. So if all the weights are, so if all the inputs are 0, then the neuron, how willing is it to fire? Okay. So if the inputs are there, and if x1 and x2 happen to be positive, then that will be even more activated, right? That neuron. So, but if they are 0, by default, what propensity do they have to fire is what the bias tells you.
So bias can never be 0, right?
Sorry?
Bias can never be 0.
No, bias can be 0, right? Bias is a learnable parameter. So bias can be 0. It depends on your data and the network architecture. Some bias terms may end up being 0. So if bias is 0, it means that there is no, the neuron is not inclined to fire until you give it some positive input. Okay, by default, if the inputs are 0, the neuron is not going to fire. That's what bias 0 would mean. So bias could be negative also. So bias is negative, it means the neuron is unwilling to fire unless you give it some really strong input in the form of x1 and x2. Okay, so this is the bias. So okay, so I hope this is clear. Now what we have been doing is called a forward pass, right? Forward pass, the idea is if you give some input x1, x2, propagate that in a forward direction, take the values from here, pass it to the first hidden layer, pass it to the second hidden layer, and finally get me an output. That's called the forward pass. Okay, so now finally, right, when you come here, this is where things get slightly different. So this is two times the hidden neuron's value here, minus 1 times the hidden neuron's value, plus 3. 3 is the bias, right? Now, depending on the problem you're solving, the activation function for your output neuron can be either linear or sigmoid. Okay, if it is linear, linear means you just leave it as it is. So g of x is x. Okay, it's actually, you can, the better term would be identity. So, but then if you see linear, it means that you are just leaving the input and not modifying it in any way. Okay, so when would this be used? When do you think a linear activation would be used? What kind of problem? It's classification, regression.
Regression.
Yeah, regression, right? So why do you need that? So for regression, remember that the output can be any real number. Okay, so you should not constrain it. So if you use ReLU, for instance, that will only give you values between 0 and infinity, right? So it won't be able to produce negative values. So that's not good for regression. If you use sigmoid, it's even worse. It will only give you values between 0 and 1. Okay, so both are problematic. So linear is what you go for. So you use sigmoid for classification, right? So similar to logistic regression, right? So sigma of W transpose X, here it's W transpose X plus B. That's the only difference. Okay, so regression you use this formulation, and binary classification you use this formulation. Okay, so for regression, y hat, the output neuron directly outputs the regression value. Okay, for a classification problem, however, it outputs not the label, predicted label, but the probability. Okay, is that clear? So the difference between,
Can you repeat? Means what you said about probability?
for a binary classification problem, the network outputs a probability.
Okay.
For regression, it outputs the label itself. So actually, there's a slight abuse of notation. I am using y hat to mean the probability in this case, not the predicted label. Okay, maybe I should have used some other symbol here, but it's okay. Okay, is that clear? Depending on what your problem is. So if you want to solve a regression problem, you will choose a linear activation function. If you want to solve a binary classification problem, you will use a sigmoid activation function. Okay, so that is
ReLU we don't use na in our
no.
output neuron.
In the output neuron, no. Yeah. Okay, so this is regression. So once you do a forward pass, you can now evaluate the loss. So loss is difference between the predicted label and the true label square, right? This is squared loss for regression. For binary classification, we just saw this, right? Cross entropy. Whatever we saw with logistic regression, same thing. So minus y log of y hat minus 1 minus y log of 1 minus y hat. Okay, so this is forward pass. So once you have the loss computed, you can now take the gradient with respect to the loss and use gradient descent, right? So that's what we'll do. So that's called the backward pass. So what you do is just a simplification. If the network has, in this case, there are 20 parameters, right? So 14 weights and 6 biases. So you put all of them together into a one vector, you call that vector theta. So this theta will be in what space? It will be in R20. Right? So theta will be in R20. So this is a 20-dimensional vector that will be your long elongated parameter vector. So you need to take the gradient of the loss function that you just computed with respect to this theta, and you have to do gradient descent. Okay, so simple gradient descent. Now there is an algorithm to find the gradient of the loss function. In the case of neural networks, that's called backpropagation. Okay, it's a very, very popular algorithm. So you'll study more about this in the deep learning course, right? So this was popularized in the year 1986 by two scientists. So there's a one of them. I'll give you the name of one of those scientists. So Hinton is Geoffrey Hinton, whatever you want to call it. He's one of the pioneers of this whole neural network revolution, and he popularized this algorithm called backpropagation that is used to find the gradient of the loss with respect to the parameters in the case of neural networks. Okay, so it's called backpropagation because the gradients are kind of going to flow back. So you're going to use the gradients in one layer to update the, or rather to find the gradients of the loss with respect to the weights in the previous layers. Okay, so it's basically what chain rule. Okay, for those of you who are interested, this back propagation algorithm is just chain rule. Okay, chain rule for multivariable functions. So this is like a function of many variables, right? So it's a function of 20 variables. So you have studied multivariable calculus in Max 2. So this is just chain rule applied on a large scale. Okay, but for our course, it's enough if you know that this thing is called back propagation and we use gradient descent. It's, if you know this much, it's enough. Okay, so that's
Theta t is what, sir? The theta t is actually a single vector or what?
it's the weight vector at time step t,
So
not the
out
weight.
of all the theta that you created, you are just taking the w's and using it for this.
No, no, not the. You're using the whole thing, right? So this has w's and b's.
Huh.
So it's the entire parameter, all learnable parameters. You're putting it inside theta, and you're calling it theta.
Okay. So t means the time step or the
Yeah,
iteration number.
yeah. Okay, that's called backward pass. Now, so far we have been looking at regression and binary classification. So finally, we come to multi-class. So assume that you have three classes. Okay, 1, 2, 3. So this will be your. These are your, I think, activation values. I don't know what I put here, but let me see. Okay, so is this there in our syllabus? I think this is also there. I'm not very sure, but I think it's there. Okay,
So
so
computing parameters of neural network is there. At the last lecture is that only. After that, just the summary of the course is there.
right. So this is, let's just quickly spend some 5 minutes on this. So this is called a softmax function. Okay, so what you do is it's a way to convert your, these are your values, right? So these are your activation values. So sorry, the values that are computed at these three neurons. Okay, now you're not going to use a sigmoid here. Okay, in binary classification, what did you do? You use sigmoid activation here. Here, what you're going to do is you're going to use something called a softmax function. Okay, so that converts these three values into probabilities. That's what it does. Okay, so it's
So for
this.
classification also, we were doing the same thing. We were finding the probabilities there.
Yeah, but that was done using sigmoid.
Hmm.
Sigmoid is not going to. We are not going to use sigmoid here. We are going to use what is called a softmax activation function.
Okay.
So that, so this is, there's a typo here. This should be e power z3. So the e power z1, z2, e power z3. And if you actually think about this, if you add y1 hat, y2 hat, y3 hat, what do you get? Y3 hat, that is equal to,
One.
that is equal to 1, right? It's a probability distribution. So when you use sigmoid also, you got probability distribution in some sense, but here it's very clearly a probability distribution over the labels. Okay, so This is what? This is the probability that the predicted label, so the label is class 1 given the data point. This is class 2 given data point, class 3 given data point.
Sir,
Okay.
what will be the z that we will put in this equation?
So whatever comes here
Where?
from this neuron, you will do some W. So W into H21 plus, so let's say W1 and there is a W2. So W2 into H22 plus B, that will be Z. So the linear combination
W1
is Z.
H21. W1 H21 plus W2 H21.
H22
H22.
plus some B associated with this, that will be Z.
Okay.
So basically, at the end of this, I will calculate 3 probabilities, right?
Yeah, 3
And
probabilities.
then whatever is the highest, that will be my prediction for the class.
Right, yeah. Okay, so these are the 3 probabilities. So this is called a softmax, sorry, one hot encoding. So exactly one will be, so if you have 5 classes, exactly one value will be 1, rest of them will be 0. Okay, this is similar to the encoding that we used in naive base, right? So for text data. So if a word occurs, then it is 1, everything else is 0, something like that. Okay, where the number of words, where that was the size of the vector. Okay, so this is what is called a categorical distribution, right? So this is not a Bernoulli distribution. This is a categorical distribution with 3 categories. Okay, and you can visualize this as tossing a dice. So
can you think of this like a if you're analyzing a bunch of text, real news, fake news, or maybe we don't know, right? There are 3 processes.
right.
So we are kind of reading an email or an article, and we have built a neural network.
Yeah,
It
yes.
predicts, and then it can end of the day it will tell is it real or is it fake or is it maybe, we don't know.
Yeah, exactly. Yeah. Okay, so that can be one way of thinking about this. Right, so this is multi-class. So there is a loss function, right? So you have to, just like you had binary cross entropy for binary classification, you have what is called categorical cross entropy. It's very, very similar. Okay, so instead of, so it was minus y log y minus 1 minus y log 1 minus y hat, right? So instead of that, you'll have log y1 hat, y2 hat, y3 hat. Okay, so there's a question on this in graded assignment. That's why I'm doing this. So one example, so if you have true label as this, and if your predicted probabilities come out to be 0.2, 0.3, 0.5, how do you compute the cross entropy loss for this? So you, what do you do? It is minus log
minus 0 log base
First
2
one will be 0.
0.2
Second one 0 and third one will be
0.
0.
Okay, so basically these two will vanish, right? So you're only interested in only this quantity will stand out. Okay, so the cross entropy loss is very simple. What it's telling you is look at the true label. So the true label here is the second class, and find out how your neural network is performing on that true label alone. Okay, rest of it are you don't care about. So this just boils down to minus log the predicted probability for that true label. Okay, so categorical cross entropy simply becomes minus log. So be careful. Sometimes it may be log to the base 2. Sometimes it is e. I don't know what is given where, but so let's say in this case it is 2. So minus log 2. You can in fact call this y hat of what subscript can I add here in general? I can actually call this y. Okay, because that's what you have computed here. This is the subscript y hat of y hat subscript 2 in this case, because 2 is the, okay, so I know it's like all this is very confusing because y is a vector here. So I hope you understood what I meant. So
Sir, yi can we take, no? Yi.
Yeah, correct. You are right. Yeah. So yi might be, well, yi. So this itself is actually some yi, right? So, yeah, it's kind of. I hope you got the idea, right? So I'm didn't express it very well, but it's like minus log of the predicted probability corresponding to the true label. So I'll just call it true label. Okay, whatever true label you have, what is your predicted probability corresponding to that minus log of that value? That's the categorical cross input. Okay, so is that fine? Categorical cross entropy. So that's all there is to neural network. So what you have to know mainly is going back. So you need to know how to work with the given neural network architecture. So you must know what kind of activation functions can be used, which will go where. Okay, so for regression, what can you use? For classification, what can you use? How do you do a forward pass, right? So if some inputs and some weights are given here, and you are asked to do one forward pass, you have to be able to do the whole thing from input to output. Okay, so what else do you need to know? You need to know how to calculate the loss function given the output labels and the y hat values, right? So that you must know. You must also know, you don't need to know this part because this we have not covered in detail. And you must know how to compute the softmax activation. If you're given Z values, how to compute this, okay, and that cross entropy loss. Okay, so that's roughly what you have to know. Right, so let's
Sir, before you stop, means what is the difference between binary cross entropy and categorical cross entropy? Means what is the major difference? It looks the same.
just one second, once again.
I think binary has two labels. I mean, two levels, 0 or 1, where the categorical can have multiple, 3, 4, 5, like that.
But they output the probability itself, no?
Yeah, logistic is a special case of softmax, where number of levels are 2.
Yes.
Okay, sorry, yeah. Okay, so yeah, so this is what we have now. This just slightly beyond the course, so we have completed. So what happened in the last 10 years is something you must know because you will soon be going into deep learning. I hope most of you. So you have, there are three things that actually triggered this whole deep learning revolution. One is the presence of really large data sets. Okay, so this is what is called, that's one example is this ImageNet data set. So there are roughly 14 million images there. Okay, so data sets, they form one component. The other one is what are called deep neural networks, right? So what we have just seen is a neural network. Now if you stack many layers together and if you change some details in the architecture, you get deep networks. This is another very important part. And then you have more compute, right? So there is much greater computational power in terms of what are called graphic processing units, right? Which are tuned to do normal computation for science, right? So not, and not just for gaming or rendering graphics. So these are called general purpose GPUs. So there are three things: data, compute. So this is data, this is compute, this is better algorithms, right? Better architectures and better algorithms. So these three together have spawned what is called this deep learning revolution. So it's roughly 12 years now. So in 2012 is one very important paper came out. It's called AlexNet. Okay, so this came out in think from the University of Toronto, if I'm not wrong. So from Canada. Okay, so they set the stage, and from then it has been a big revolution in data science and AI. Okay, so and final thought,
Professor Jeffrey
yeah,
Hinton, right?
yeah,
Hinton.
Hinton's group.
Yeah,
Yeah.
yeah.
Okay, so what is MLT in our course? What we have done is to compress whatever has happened in the 12 weeks. You have been given a data matrix X, okay, that is X, and then you use whatever model you want, whatever model you like, and then choose this is a model family, right? And you just choose the best model using cross validation. So that's the overall theme, okay, and out comes a classifier. Right? So X goes in MLT, out comes some classifier. So what we have learned is what is happening inside this box. How does X turn into a classifier? So what does it mean to say that we are learning from data? So that's what has happened. So of course, this is X comma Y. In you want to be very specific. So that's this course. Now there are many things which we have not done, as the professor also mentioned. So I'll just quickly go through this. There's this cross-industry standard process for data mining. This is one standard, and roughly what happens is if you are given you start with a business problem, right? So usually problems come to you that way. So you are not going to be given data right away. So you'll be given some business problem, and there might be some data associated with it, or you might have to generate data or gather data from the business, right? So yeah, you need to understand data, what all data is available, what all can I gather, okay, and then you have to prepare the data. So what features to choose, even before that, what columns to include in your Excel file, what columns to drop, and all this you have to do. And then once you have the data, you will start modeling. So this is what we have discussed in our course. The first three items we have not at all discussed because that's outside the scope. Mainly we have discussed how do you apply a model on top of existing data. Okay, and then you have to evaluate the model. You have to see how well it is performing. If it depending on that, you will go back and fine tune your business problem, right? So if it performs really well on some segment of data, you will say that I'm getting good results. So, but if it's not performing on some segment, you'll have to go and change your problem statement a bit. Okay, and once you see that the solution is kind of good enough, you can deploy your machine learning model. But it's not enough if you deploy, right? So once you deploy, you'll have to monitor it. You'll have to see if it is improving over time or if there are any bottlenecks. So you have to take care of that. Okay, so different roles come into the picture here. So this is the life cycle, right? This keeps going on and on. So you have different roles. So those who deal with data, they are going to be called data engineers. Those who prepare and help with creating the data, cleaning it, and pre-processing it, all that, right? So of course there will be some intersection with the person you call a data scientist, right? So data scientist may also have to do a lot of pre-processing. Okay, he might also have to sit in the business meetings and try to understand where the data comes from and all that, right? So, and finally, you'll hand over the data scientist will hand over the model to a ML ops engineer who is responsible for deploying this model onto the cloud, allocating resources on the cloud, and making sure that these APIs are exposed to the client, okay, and all that. Okay, so all these things, there's so much more that we have not covered. So yeah, so that's the end of week 12.
So will this course, like the diploma only, will it cover the deployment and monitoring?
No, unfortunately not. So in MLP we will discuss the coding aspect of what we are doing. So that will happen. Deployment and monitoring will not come in the diploma at least. Okay, but there will be, so you with what you learn from the programming diploma, you can kind of put these two things together. I hope that can happen. So with whatever you learn in this modern application development, I hope some aspects of it you can kind of Mix and match.
Sir, have we completed?
Yeah.
So I have some questions regarding previous term question paper, if you allow me to share.
Okay.
So this question, sir, uh, it's visible, right?
Yeah.
Huh. So it says that we have applied a ADA boost algorithm to run on a data set using decision stump as weak learners. Okay, just what we saw yesterday. And it says that, as you said, minimize the weight means basically we take the data for the next iteration. We take those data points which have the means highest error, right? Means basically it says it minimizes this equation. So I understand this option. It's totally fine if I draw this margin here. Huh. But I'm not getting how this is right.
Um,
Am I audible?
yeah. So what is happening?
Can you draw the
This
line
thing.
from
This
3-1
is
to 3-4? Where is 3-1? 3-1 is
3-1 is here.
okay, and 3-4 is
Here.
okay. So you are basically drawing a vertical line there.
Huh, I understand that, but isn't that the case that it will have large amount of errors here? You can see that, like, even if I say that this is the right point, okay, then these all data points are wrong.
Three
And if
wrong
I
on
say this is
the correct.
Hmm.
There are 3 wrong on the right hand side, and then
Yeah, so there
3
will
on
be a large
the
training
left
error.
side. So 6
Huh.
errors total.
So best possible that I could think was like this, because in this case, this is a error, this is a error, and this is a error. Now, if I select this one and this one, it makes sense that it will also cover this one, right? So I take this one, that's totally right. But how this is the right answer, that I want to understand.
Which points? What is the question asking? Which points will be assigned equal weight?
Equal weightage, yes.
Create the training data set.
Hmm.
Okay, why are we choosing training data set again? I don't understand.
I think it should be, you are saying right this. So for each iteration, it is saying, right? For each new weak learner. So we are creating a new weak learner. So means earlier, as you said yesterday, that we will assign same probability to each of all, right? 1 by n. Now, as we move along, we will identify which are right and which are wrong. And then we will process it like e to the power alpha to the power something like that, right? Minus alpha or plus alpha. If it is wrong, then we will add plus alpha, else we will add negative of alpha, right? So if we add plus alpha, then this data point, and this data point will have same amount of error, right?
First of all, what is the first decision stump?
This is the 3, this line that I drew. This was the best I could possibly come up with.
Okay, 1, 2, 3. 3 misclassifications, is it?
Yes.
Okay, so that means those 3 are going to be boosted. So when the new so second stump, which pair of points will be assigned equal weight to create the training data set? I don't understand what is meant by what are we creating here? We are not creating any training data set, right? So it's already done.
We are creating a classifier, I guess, but something is wrong with this question, I guess. It says to train a second decision stump, which pair of point will be assigned equal weightage to create the training data set. So we will work on those data set. Means I think it means that which one we will take as boosted and which we will not take as boosted.
Okay,
Or
so
reduce.
1 1 and 1 2 1 1 1 2 and 1 4 are going to be boosted, right? If
Yes.
you
So this is okay. This is
Okay.
okay. I did it. But this 3-1 and 3-4, how they are going to be boosted or not boosted,
So
whatever.
after doing the first iteration, when you have those weights, okay, that line. So after that, you will update the weight for each points, and after that, you will have a second decision boundary, right?
Okay.
So when you will draw, you can't say by drawing now that that boundary is good or bad. Ultimately, at last, we will see that which reason is going to contribute for the final reason. So after in the first round, you have that weight. Based on that weight, we will boost the points, and you will have to come to a boundary.
Okay. So what will be the second boundary then?
So we can perform the calculations after that. If we have the first that boundary and we have that weight, we will boost each point, we will calculate, and we will have that second boundary. So claiming like this that we cannot have that as second boundary because that will have 5 error or 6 error is not going to make sense. Ultimately, we will see at last to which reason it is going to contribute.
But it says for the second decision stamp only, not
Hmm.
for all.
One thing, Karthik sir,
Yeah.
claiming now that if you draw that second boundary, it will have 5 error or 3 error. Will it make sense? Ultimately, at last, we will decide na, that which reason it is going to contribute.
Yeah, but I think they're asking before you train the second stump,
Huh.
which pair of points will be assigned equal weights. So see, the 1
Uh,
1 and 1 2 are going to be boosted. 3 1 and 3 4 are going to be, they're going to come down in weight, and they'll be coming down with the same, by the same factor they'll come down, right? So maybe that's what they mean. Can you go to the wrong option? So the 2 2 1 2.
And after that, we will look for the lines with the least error as much as least we can do.
Uh, yeah, but can you go up? So what is 2 2 and 1 2? 2 2
Uh,
is
2-2 is this one,
okay, 1 2 is
this one.
okay. So they are not going to be having the same weight, right?
Huh.
Because one is misclassified, another was, so that therefore that is wrong. Can you go to the next wrong option? 2 2 and 1 4. That is what 2 2 and that is correctly classified. 1 4 is misclassified, right? Therefore that's also wrong. I think that is all they mean. So if you compute the weights, so the weights will be what you'll do e power alpha into 0.3, right here. 0.3 by
Point 3.
0.3 is, sorry, not 0.3. 0.3 is epsilon, and then you'll do half ln 1 minus epsilon by epsilon, will get some alpha. So you'll do e power alpha into point whatever. So what is the, how many points are there? 1, 2, 3, 4, 5. So whatever, right? Whatever number of points, you do 1 by that into e power alpha for some, divide by sigma, all that, right? So yeah, but the question is correct only. So before you train the second stump, what are all the, what are the pair of points which have the
Equal
same weight?
weightage.
So that's correct only, I think.
This second one, is it because that lie on the center of the line?
No, no, 3 1 3 4, both are
Huh.
going to get boosted. So both are going to get they're going to come down, right? Their weights. If 3 1 is
Huh.
correctly classified,
Huh.
3 4 is also correctly classified.
Hmm.
Therefore, their weights will be e power minus alpha into 1 by n.
Okay,
So
okay,
both
okay,
of them
yes.
are going to have the same.
So,
They are
sir,
going to have
same
equal
could be
weights.
same can be said for the 4-1 and 4-4 also then.
Any pair of points, so 4 1 and 4 2 are also going to have same weights.
Okay, in that sense, yes, then this question makes sense, sir. And here this point,
Okay, so yeah.
these were working in inverse, right? As you said, like if we increase this, this will decrease. This is the
Mm,
regularization term, this
right.
part, right?
Regulation and hinge loss, right?
And this is the error term, the bribe that they will pay, right?
Mm, yeah.
So
Smaller
they
one
were,
C.
huh. So that's why I asked this question yesterday, means how C affects.
Yeah,
So it
smaller
says,
value of C allows for a larger margin. That part is correct. So smaller value of C means your margin can be large, but the next part may be incorrect. So potentially leading to, no, it will lead to more misclassifications, right? Because the margin is large.
yes.
There is,
Mhm.
there,
Okay.
More
So I have to take the
misclassification.
entire thing.
yeah, but
Means they are two separate. They are two separate things. They are just I mean, same.
No, it is asking that can we conclude from that?
Oh, so we can't.
Uh,
so I won't call it misclassification. Instead of calling it misclassification, better to call it margin violation, right? So if you
Huh.
have a large margin, then there
Hmm.
will be lot of points which violate the margin. So
Yes,
will
yes,
all of
obviously.
them actually get misclassified? We don't know.
Okay.
Potentially
So,
leading to a lot of margin violations. I might rephrase that
Mhm.
statement like that.
Okay. And one last question at the very top. There is one question which I'm not understanding, means how to process this. Yes, this question, sir. W1 and W2 we have to calculate, right? So,
So you just have to draw 1 root 3 minus 1 root 3 and find out the two range. You have to just draw this classifier such that x1 will just be predicted properly, and you have to draw a plot. So I kind of have an answer. I solved this, and let me check if I have that. So
okay.
where was this? This was in term 1, term 3 actually.
Sir, this question is from the last PYQ only.
Last PYQ maybe, but then I remember framing it a long time back.
Okay.
Yeah, so
Basically, what this question says means that I want to understand. Like,
So I guess how much can we rotate the decision boundary without affecting our or without changing our prediction? So what is a
okay.
that is what it is trying to say. At what angle? So we started with that angle theta, but how much the theta can it be 30° to 180 50? Because then even if I can pick any classifier
Mhm.
at that angle, that will give still the correct classification. But if I
Any
go below
classifier?
30 or yeah, that's what it basically say. What's the flexibility? So I have flexibility, choosing any classifier which falls into this feasible region.
yeah, so I don't have the solution with me now, but yeah, you have to draw. Basically, you have to plot it, and then so
We have to plot this, sir.
you have to plot those 2 points and also the decision boundary. So the decision boundary will be perpendicular to W. So you have to first plot the boundary in such a way that it passes through each of these points. That will be like the limit, right? So if
Okay.
you rotate the boundary slightly, one of the points is going to get misclassified. So you'll have 2 lines passing through these 2 points, and then W1 and W2 will be,
So this is actually the y coordinate, and this is actually the x coordinate, right?
So we have to think like a polar coordinate, right? So we have got, there's a radius and theta is the angle with respect to the x-axis, right? So if we put 1 and root 3, so you can clearly see it's angle, 30°, like sine by cos, right? So they have given tan 60 is root 3. So tan is sine by cos. So the first coordinate is cos, second coordinate is sine theta. So you can clearly see the first value is x coordinate, second one is the y coordinate, like a tuple, right? So that actually tells us.
Excuse me, this polar coordinate, I don't know what is.
I mean, it's the same thing, Okay, fine. You can represent as a x any point in a graph. You can represent as a x comma y, where x coordinate, y coordinate, or if I think there's a line radius r from the origin and the angle it forms to the x-axis, I can represent. I think we learned in Python class actually.
Cos
How
theta
to
comma
represent in a coordinate system and all that. How to convert and all that. Long time back.
Okay, so you're saying that means
Yeah.
I can represent
Correct.
that like
Yeah.
this.
So I can reach any point in this r square plane by using r and theta. That's all we're saying. So anyway, going with that method, I think we can clearly see if I put these 2 points, what are my, the V shape that will come out, right? That's my feasible region. You can visualize it geometrically.
the reflection.
Okay.
Second one will be the reflection.
Okay. Then I have to go through this question. Rest all I am already done. Here, sir, one question. This we will not classify as like this is wrong. I know, but we can say that it's a support vector, right? Because still here we want it, and alpha will be greater than 0.
For being to be support vector, we have to follow that it should be less than equals to 1. So for the support vector, it has to be.
No, basically, whatever yesterday sessions are said, no? So these points we will take as like, means these are the only points which will move till here because we are giving bribe them, we are giving bribe in such a way that it just reaches this. That's our goal, right? And at this point, by equations which sir showed yesterday, it will alpha will be greater than 0, right?
So which one? So this is misclass. So if that green point, the right side is the positive hyperplane, right?
This is red. This is positive, I can say.
Okay, so that blue, what does that blue color mean? Some
It's
other
negative. It's negative. It's
okay.
negative.
The moment you see something is misclassified, that has to be a support vector, right? So
Okay.
all misclassified points are support vectors by like alpha equal to c for them. So can straight away conclude that if it's misclassified.
Sir, this is right classified, right? But we will again give the bribe till here only, so we can conclude that this can act as a support.
Is classified or classified with
Margin less than or less than 1, right? So
This is classified as less than 1. Yeah.
so
Actually, it's 8, right? Here it's 8. So less than 8, I can say.
yeah, they're giving 8 and all. It should be 1. It should always be 1. It should not be 8. So we don't do 8 in our course. We just do W transpose X equal to 1 minus. Oh, okay.
Yes.
They are teasing us, is it? So that okay. But I don't know why. Can you go up? What is the question stating?
It simply says this is the diagram and which of the following statement is true about this data set.
Okay, why is it 8? I don't see. It should not be 8. They should not have drawn 8. So it's W transpose X equal to 1 minus 1. On, even for soft margin, it's the same thing.
Yes. And this is a soft margin case only, right? Points are lying inside this.
Yeah, but why suddenly come up with 8? I don't understand.
I also. I think this is actually, in general, this is any value we can say like B.
So if it is 8,
also there is minus 8, so yeah, makes sense. We can think of it as like -1.
So if they have provided us with 8, then to solve this problem, like we have to do it like 8 by norm, and we will have to redraw that decision boundary, that margins.
So the margin may not change. So see, I don't know why it's called 8. So if there's a follow-up question, at least it makes sense. Is there a follow-up question? It says
no, sir, there is no follow-up question.
Okay, just that question, is it?
Yeah.
Okay, I don't understand why it has to be 8. So it means let's just change it to -1 and 1. It doesn't make sense.
Because if it is 8, then we need to normalize it, right?
Yeah, so we should not give, if the one who is creating the question will not give a 8 there, because what does that mean, right? So it should mean something, no? Which W transpose X equal to 1 minus 1 is what we have been doing all along, and suddenly you come and throw 8 there, it's confusing. So
I think they wanted us to think that we have to normalize.
yeah, so perhaps, yeah.
Okay.
Okay. So is that all? Shall we close?
This question, do we have to create the X matrix and then calculate the variance, XX transpose? Because it says covariance matrix, right? And these are all eigenvalues.
Okay, so the eigenvalues satisfy this system, is it?
Ah, yes.
Okay, yeah, you have to solve for lambda. You have to solve for lambda and
What I did was 2, 1, 3. I created a matrix for X and lambda separately and Y's also. And then I tried to calculate just the X values to get the covariance matrix.
X is not needed, right? You are already given lambdas. No, with lambda itself, you can find the variance. No, total variance is just sigma lambda I. No,
Sigma into lambda, yeah.
no, sigma. So summation over all lambdas, right? So
So
lambda
all
1
these
plus lambda 2 plus lambda 3 will give you whatever you are looking for. So just solve that system and find out the sum of the solutions of those three components.
Okay. But here it says means okay. So lambda 1, lambda 2, lambda 3 summation should give me some value, and I have to solve this equation using RREF or something, right?
Yeah.
Okay.
We
got it.
basically can we not do row reduced echelon form? That will give you the answer.
We can do that.
Right. Yeah.
So numerically, lambda captures the number which is same as the variance, no?
Yeah, it is the variance. Yeah.
Variance, it captures the variance. Yeah. And last question is means neural network. I had this doubt, but I solved it. Means I will solve it now. Means how you have stated. So first, we have to create a graph for this to understand, or
Yeah,
just.
better. Yeah.
There one thing you did not cover today. Maybe if I have a network, I got let's say three nodes in the input layer. In the hidden, I may have like 4. So how many possible weights are there in the entire network, right? Stuff like that.
I think you sir covered that, no? Starting at the very start.
I'm just starting. Okay, I joined 5 minutes. Sorry about that. I'll go through the video.
Okay, sir. So that's all for this.
Okay, then. So we'll meet for revision next week. Yeah.
Right. Thank you very much.
Thanks, sir. Yeah.
Okay. Thank you.